Testing. Okay, good morning to everyone. So how's your weekend? Huh? Good. What do you guys do? Huh? MPU. Okay. I haven't finished marking your assignment yet. Some of you haven't. Some of you was late. So I will give you back on Wednesday. Again, Wednesday. And then we will discuss it. And then so that you can prepare for Monday exam. Okay? Okay. So next Monday, please come on time, all right? So that we can start earlier. Okay, so maybe please come at 8:50 to prepare. Okay, so that we can start at 9. Okay, I will give you some reading time before we start, and then we will have about 1.5 hour exam. Okay, so please come at 8:50 next Monday so that we can prepare earlier. Okay, and then we will have some reading times so that you can read first and then ask me some question if question got problems before we start. Okay, clear? I'll make an announcement also. Okay, so please come earlier next week so that we can start on time, finish on time. Okay, any question or not from last week? So my lecture left a lot of exercises, right, for you to do. So please do them. Okay, if you don't understand, you should ask. Okay, if you keep everything to yourself, I cannot help you. Okay, and the reason why I ask you to do a lot of exercises yourself is because for these hard concept, abstract concept, you really need to do it hands-on. Okay, you cannot just listen to what people say because you don't know what is really going on if you don't do it. Okay, that's why I will have some part I do it on the spot together with you, and then some part you have to do it yourself. Okay, otherwise it's different. It's really different. You can experience from what you learn by listen to people and what you learn by yourself is different experience. Okay, I need you to practice getting the knowledge yourself. Okay, but at the same time, you have me. Okay, so if you cannot get it, you still can get me to get it. Okay, this is really different when you go into real life. Okay, there's no one, maybe most probably no one to guide you. Okay, so you need to guide yourself. Logic. Okay, and actually I posted up. I'm not sure how many of you realize there's one note I post out on Moodle is done by physics students. Any one of you have a look of that or not? Did any one of you see it? Post on Moodle. I post on week 5. There's one note I posted up by this student here, a physics student. Why I posted this out? Because I found out that his note is very organized and systematic. Okay. Why is it so? Let me show you. Okay, so he's a physics student, right? Okay, but he is learning. What is he learning here? I forget what he's learning already, but there's a subject called topology inside his course. Okay, so topology is related to maths, and you can see that there's a lot of analysis here. Okay, and then why I'm saying this is a good note, okay, because this note is succinct, short, okay, and clear. Why is it clear? Because you first put what is the definition, okay, regardless what's the whether this document is accurate or not, but this is systematic, okay, clear. Why? Because you start with a definition, okay. After you have a definition, you have examples, okay. After examples, you will see what's the property that a limit point will take. Okay, so everything is like match, okay, link, okay, and then you will have theorem, okay, so on, right? See, closure of set. So what's the closure of set? Example, okay, example, okay, and then what's the property of a closure? Proposition, okay, definition, example, proposition, proposition, proof, 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 example, proof, definition. So when you read it, it is smooth. Okay, you know what is going on. Understand or not? Okay, so this is how you learn mathematics. You need to learn a new things. Okay, what example represent those things, and then what's the property that the new things take. Okay, I hope you can try and have a read on this note here. Okay, so I hope you can develop the same. This is by a physics students, not a math students. Okay, so so um so why he developed this? Okay, I asked him why he can develop this kind of skill because he never learned pure maths or never learned logic. Okay, by any courses. So why you have this kind of thinking? I asked him. You know what he say? You guess what he said? He said, I always met bad teacher. I always learn by myself. Learn by himself. Okay, if you have an experience of learning by yourself a lot, this is what kind of thinking you will develop. This is the kind of thinking you should develop. Okay. So you have lecturer to teach you. Okay. You also need to learn by yourself. Otherwise, you cannot develop this kind of thing. Okay. Yeah. Okay. Yeah. Don't too rely on teacher. Okay. Otherwise, you will be miserable. Okay. Okay. So last week we stopped at the correspondence theorem. Okay, using coset. This week we will finish up finitely generated abelian. Okay. So first of all, so we talk about groups, right? Any groups in your mind or not? Any examples of groups in your mind? Can you think of any group? Can you tell me? Sorry. Z, the integer. Okay. Any other group? Symmetric group. Good. Any other group? R. Sure. Real line. Okay. Any else? Zn. Sure. Okay. So let me put here. Zn here. Integer modulo n. And then? Huh? GLN. Good. So you put real number together. Okay. Organize them as a matrices. Invertible matrices. Any other? SLN. Okay. So these are the normal subgroup. Okay. Anything else? Cyclic group. Okay, good. Cyclic group. Hey, how should I write cyclic group? So let us denote Cn. Okay, cyclic group with order n. Okay, where can you find cyclic group? You take any element in the group and then you compose with itself. Okay, to generate the cyclic group. Anything else? Hmm. Anything else? Abelian group. Okay, good. Abelian group. So who are abelian group? Okay, so good. So abelian group is a category of group. So, eh, so the first line I put here actually are all examples of abelian group. Okay, what does abelian group mean again? The law of composition is commutative. Okay, AB equals to BN for all AB in the group. For all the abelian group here. Okay, so the bottom is examples of non-abelian group. Okay, matrix multiplication is not abelian. Uh, function composition is also not abelian in general. Okay. Anything else? Alternating group, good. So this is a normal subgroup of Xn. Okay. So they are the kernel of some homomorphism. Okay. So last time we proved that every kernel is normal. Okay, but we haven't seen yet why every normal is a kernel of some homomorphism. It will be done this week or next week. Okay. Anything else or not? Anything else you can think about? Okay. Right. Okay. So out of these abelian group, right, which one is finitely generated? Do you still remember what does finitely generated means? You can write it as a group with finitely many generators. Okay, you just need finitely generators to create the whole group. Okay, under the law of composition. So out of these four, which one finitely generated? Huh? Any idea? Which one is finitely generated? Sorry? Or except R? Okay, so all except R. Okay, so all except R. Let me circle them. Okay, all except R. Okay, so if all except R, so tell me, what's the generator in Zn? What's the generator in Zn? How many generators you need to generate Zn? 1. So who is the 1? You just use 1 to generate it. Okay? So you just add 1, 1 plus 1, 1 plus 2, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1. Okay, right. So this is the piano axiom, right? How you build 2, 3, 4, 5. Okay. How about Z? Z also use 1. Okay. So this is how piano axiom start, right? Okay. How you define 2 is 1 plus 1. How you define 3 is 2 plus 1. How you define 4 is 3 plus 1. Yeah. How about Cn? Generated by who? Sorry? By the group generator. Actually, there's a characteristic of that that generator. You can describe this generator. Not exactly. Not exactly. Not any of them. When it is the X such that the order of X equal to the order of the group. Right. Okay. Because you need to create n different elements. How do you create n different elements? Okay. You need to have an element with order n. Okay. Otherwise, it go back to identity too quick. Okay. So you need to have an order n elements to create the group. Okay or not? Yeah. Okay. Yeah. Wait, let me think a little bit. So should I give you an example? I know you like examples. So let me think. So what is 2, 1, 2, 3 composed with 1, 2, 3? This is always even, right? This is always even. Yeah, never mind. Okay, how about we leave it like this first? The order of X is equal to the order of the group. Okay, so this is the generator of X, of Cn. Maybe we'll see example later. Okay, we'll see example later. Okay, so so what can you see here? You see, finally generated abelian group is like Zn, Zcn. Okay, something like this. How about in general? Okay, so how about in general? So definition. Finitely generated abelian group is a group. Okay, first of all, is a group where its law of composition is abelian. Okay, and how about I write like this? Call it G. Okay, G will be equals to the generating group by x1 up to xn. Okay, where n is in z greater than 0. Okay, so it's finitely generated. Okay. So we want to describe every such group. Okay, we want to describe every such group. If you think again, actually this group is actually quite normal. Why is it I say quite normal? because we want to have an easier group. Okay, we want to have an easier group. That means what group are easier? For example, is the integer
Is common or
common. Yeah, common. Yeah, common. Yeah. Okay. So where did I stop? So I mean this group is how to say is the first thing you will think of. Right. For example, how you do computation in integer. Can you just sort as you like or not? Can you calculate 2 plus 3 as you calculate 3 plus 2 or not? Can you calculate, for example, in real 2 times 3, you can go and calculate 3 times 2. Do you automatically sort the order on? Right. Okay. So this is a natural world you live in before. Okay. It is obedient. You can just swap. It's not like Sn. Sn you cannot just swap. And 1, 2 composed with 2, 3 is not the same as 2, 3 composing with 1, 2. Okay. Okay, so this is a natural world you should which we are familiar with. Okay, so we want to study this. Okay, so we want to study this. So before studying this, we need to build another new tool called the product groups. Okay, so to study them, we need the notion of product groups. So we are going to product groups now. Okay, so you want to talk about groups, right? First of all, you need to start with a set. Okay, a set with a law of composition. Okay, so what set we are looking at? So we'll define the Cartesian product. Okay, we will define the Cartesian product of set B1, B2 up to Bn. Okay, so this is a set, right? Okay, so what should I tell you to tell you about set? Okay, for example, I need to tell you about the mathematic batch 232209. Okay, what should I tell you about it? I need to tell you about the student inside there, right? Jingbo is in there, Wine is in there, CMA is in there, right? Then people will ask, their result good or not? Who result is good? Of course, it's those students' result is good, right? It's not the class. Okay, what do I mean by the class? The class mean the students. Okay, so meaning if I tell you a set, I need to tell you what are the elements in there. Okay, how does it look like? Okay, so this is a set of what? So this is a set of all ordered n tuples. Okay, so what do I mean by ordered n tuples? So you will have a bracket with element b1, b2 up to bn. Okay, and where are these? Where does this bi belongs to? That belongs to the capital bi set. Okay, for all I equals to 1, 2, 3 up to. Okay, so what do I mean by this definition here? So meaning every entries here, okay, come from a single bi. Okay, why is it ordered? Okay, why is it ordered? What do I mean by order here? Okay, order meaning I cannot just simply say 1, 2 is equals to 2, 1. Okay, I cannot swap the order. Okay, so it's ordered. Okay. So it's ordered, it is n tuples. Okay, so you pick the n tuples, entry in the n tuples from n set. Okay, can you do that or not? Why can you do that? Can you pick element from bi or not? Hmm? Hang on, Jimbo. Can I pick one element from bi or not? Can or not? Why can? Why can? Why can I pick element from BI? 3. Why can I pick elements from BI? Why can I pick elements from capital BI? Can I pick elements from capital BI? Why? Why? BI are also a set. Okay, BI are also a set. If I need to really pick a non-empty one, we should put a non-empty set here. Okay, so you see, when you look at the definition, how you read the definition, there's only one word is new here. Okay, which word is new? The Cartesian product. This is a new word. Okay, every other word are defined before. Set are defined before. Okay, ordered are defined before. Okay, and tuples are also defined before. Okay, so the only new word here is Cartesian product. Okay, so this is how you should read the definition. Okay, so what is the Cartesian product of a set? Okay, it's a set of all ordered n tuples. Okay, how do you get the n tuples from? Okay, you get from the n set that I give you. Okay or not? Does it make sense? For example, I give you a Cartesian product of Z. Okay, for example, Z cross Z. Okay, what does the elements here looks like? Okay, give me an example of elements here. 0, 0. Okay, why is 0, 0 is in here? Because 0 is in Z. Okay, because 0 is in Z. Okay, you cannot pick 1.50. Okay, for example, 1.50. It's not in here. Why? Because 1.5 is not in Z. Okay, does it make sense? Okay, okay. So, uh, so how do we denote the Cartesian product? So I give you the example already. So in general, okay, in general, we will write the product group as product set as B1 cross B2 cross until Bn. Okay, or we can use the notation of a capital product. Okay, capital product. Okay, so I claim that this set can make into a group. Okay, can make into a group. How to make into a group? Can you think of a way to compose two elements or not? Can you think of a way to make Z cross Z into a group? How do you combine two tuples in Z cross Z? For example, let me ask you, right? So let's say we have another element here, maybe 1, 0. Okay, so how do I combine 0, 0 and 1, 0? Use the same LLC as Z. Okay, so in this case here, our Z is just addition. Okay, so we can, how do we define 1, 0 composed with 0, 0? Okay, what we do is we add, okay, we add entries by entry. We compose entry by entries. Okay, we compose entries by entries. So let me put a theorem here. So let G1, G1, G2 up to Gn, okay, be groups. Okay, so let's take two n tuples from the Cartesian product of these groups. Okay. Okay, so how do I define the law of composition? Okay, how do I define the law of composition? Okay, so how do I combine A1, A2 up to AN, compose with B1, B2 up to Bn? Okay, how do I compose? How I compose is I multiply component wise. Okay, I multiply component wise. Okay, so you can see that these group a priori they will have their own law of composition, right? Maybe G1 is Z, G2 is matrix, G3 is a real number. Okay, depend on which group you live in, the law of composition will be depending on your group. Okay, but it's okay, right? Because the first term, first entry will be coming from the same group. The second entry will also coming from the same group, G2, G3, and then so on. Okay, they are all coming from the same group. So you can combine within their world. Okay, just that we see all the combination together. Okay, we see the combination together. Okay or not? From here, we build new stuff. Okay. Okay. So, so the claim is this product group is a group. Okay? Is a, and then we call that this is the direct product. Okay, so this is a very important phrase here. Direct product of the group. Okay? So this is a very important phrase. Direct product of the group. Yeah. Okay. So can you quickly see that why is this a group? What's the identity here? Okay, so who is the identity? You just pick identity from every group. Okay, because every group have the identity, so you just place them as a n tuples, right? Okay, and then inverses of an n tuples is just n tuples of inverses. Okay, and then anything else we need to check? Is it associative? Is it associative? Because you compose entry wise, right? But entry wise is associative. Associative, inverse, identity, that's all right. Sorry? Closure. Closure, automatic. Yeah. Nothing else. Okay. So it's a good exercise if you can write down the proof. Okay, whether this is a group or not. Please write it down. Okay. Please write it down yourself. Okay, whether this is a group. Satisfy all the group property as well. This is a good exercise. Okay. Write it down. Why is it a group? Okay. Write it down with a try. Write it down. Okay. At home. Okay. So let's say, okay, there's another terminology here. Okay. So let's say, okay, all the LLC are commutative. Okay. If all the LLC are commutative, okay, then we will write it as a direct sum. Okay, we will replace the product. Okay, we will replace the product as a direct sum. Okay, we'll write like this. If all the law of composition is commutative, okay, which is known as the direct sum. Okay, so these are big words, direct sum, direct product. Okay, it will be very important for the later year maths course. Okay, direct sum, direct product. Okay, very important. So I just introduced as commutative, LLC or non-commutative, but they will have some other property that these two need to take. Okay, some other abstract properties. We won't talk about it now. Okay, yeah. Yes, G can be different. So for example, right, let me put another example here. So maybe we can take Z cross with GLN also can. Yeah, we can do this. Yeah, GL2 if you like. Yeah. So what's the element here? It's like 1 with 1001, something like this. Okay. Yeah, it's possible. In fact, in this complicated world, we need this kind of thing. We need to combine a lot of things together. Okay. Yeah. Okay. So yeah. Okay. So similar idea. So we want to talk about cyclicity here. Okay. Let's look at some example, right? So we can ask whether Z2 cross Z3 is cyclic or not. Okay. Is it cyclic? So can you think how many elements in this group here? Yeah, 2 choice in the first entry, 3 choice in the second entry. So how many order pair you can make? 6, right? Okay, you can make 6. In particular, what are these 6? These are 0, 0, 1, 0, 0, 1, and then 0, 2, and then 0, 3. Sorry, no, don't have 0, 3. 3 is 0, 4 is 0, 0. And then what else? 1, 1, and 1, 2. Okay, so these are the 6 of them. Is it cyclic or not? So meaning, can the group be generated by a single element or not? Can or not? Cannot. How are you so sure? So you need to prove if you say cannot, right? There's no isomorphism you need to prove. Yeah, why cannot? Yeah. Yes. Why yes? Why yes? Why yes? Check the order of these elements, right? Can you check the order of these elements or not? What's the order of 0, 0? Just 1, right? What's the order of 1, 0? What's the order of 1, 0? The order is 2. Okay. So I'll try to write it. So I put a list of order here. Okay. Yeah. Order list here. Order here. So this is 2. This is 1. 0. How about 0, 1? The order is 3. Okay. How about the order of 0, 2? 3 as well. Order of 1, 1? Okay, I want all of you to calculate this. You have to know this example. Everyone go and add 1, 1. Add multiple times. See when you get 0, 0. Do it. Okay, do it. If you cannot see it, please do it now. Write it out. 1 is 1, 1 plus 1, 1. This is a very important exercise to see the fact. So some of you see that this is already order 6. Why is it order 6? Why you add 2 times, it don't go back to 0, 0? Why you add 3 times, don't go back to 0, 0? Do it. Calculate it. This is a very important example. Reserve got pen or not? Write it down. Otherwise, you forgot. Okay. So 1, 1 plus 1, 1 is what? 0, 1, 0, 2. Okay. 0, 2 plus 1, 1 is what? 1, 0. Okay. Not 0, 0 yet. 1 0 plus 1 1 is what? 0 1. 0 1 again. 0 1 plus 1 1 is what? 1 2. Okay. And then 1 2 plus 1 1 is what? 0 0. Okay. You see, the order is 0, but when you do the composition, all the elements drop out. Okay or not? You see it? All the other elements drop out. Okay, while you checking the order. Okay, so this reflects to what I said in the earlier case. What's a cyclic group means? Cyclic groups is generated by the element with the order equals to the order of the set. Okay, so my order of Z2 cross Z3 is 6. And then the order of the elements 1, 1 is also 6. Okay, so this is generated by the element having the same order. Okay, so this is order 6. 1, 2, 1, 2 order is, sorry, 1 is 2. So 1, 2 plus 1, 2, you get 2, 4. So you get 0, 1. Is also 6? Is it also 6? What's the order of 1, 2? So this one is for 1, 1. 1, 2, what do you have? 0, 1. Okay. And then 1, 2 plus 0, 1 is 1, 0. Okay. And then 1, 0 plus 1, 2 is 0, 2. And then 0, 2 plus 1, 2 is 1, 1. And then 1, 1 plus 1, 2, 0, 0. Yeah, it's also order 6. Okay, so meaning is what? Meaning you can also generate your group with 1. Okay, they two generate the same. Okay or not? And you see that when we checking the order, all the other elements drop out. Can you see it? Yeah. Okay. Yeah. So before you get to the order, get to the identity, you will reach all the other elements first. Okay. So this is a cyclic group. Okay. And then the other thing you can see is Z2 cross Z2 is not cyclic. Z2 cross Z2 is not cyclic. Why? Why? Why is it not cyclic? Sorry? Order 2, right? Order 2. Sorry? Yeah, element. So, okay. Yeah. So what's the order of Z2 cross Z2? It's order 4. Okay. Any order 4 element or not? No, right? Okay, so you cannot generate the group with the elements because all the elements there are order 2. 0, 1, 1, 0, 1, 1. You add to itself 1 times, go to identity already. Okay, so cannot be generated. Okay, you cannot use a single element to generate others. Okay, so you need how many elements to generate? So you need at least how many elements to generate? You need, for example, 0, 1, and 1, 0. Okay, so you need these two to generate. Okay, you need these two to generate. This is what? Okay, this is a big, looks like two-dimensional vector space. Right, a little bit. Okay, because we just have group structure here. We don't have scalar multiple. But you can see that this, you need 0, 1 to 1, 0 to generate. Okay, but in cyclic case, you just need 1. Okay. So in Z2 cross Z2, this is almost like R2. Okay, this is almost like R cross R. Okay, just that I change the field. Okay, I change the number. Okay, I change the scalar here. Instead of I can put all the R ins, I can only put that two, 0 or 1. Okay, it's like a binary word. Okay, 0 or 1, 0 or 1, 0 or 1. Okay? Instead of R. Okay, is it okay? Okay or not? Does it make sense? Make sense? Okay. So this is not cyclic because it doesn't have the element with order equaling to the order of the group. Okay. Okay. Cool. So from here, we can deduce one thing already. Okay. What is so special about these 2, 3 here? Okay. What is so special about these 2, 2 here? Okay. Try and deduce. Okay. Why I put 2, 3, it is a cyclic subgroup. Why? When I put 2, 2, it is not cyclic. Okay. Why? This order is less than the order of the group. You kind of think of it. Why? How we get to identity? Okay. How do we get to identity in each case here? Okay. We need to meet the order of the group together. Right? We have to meet the order of the group together on both sides. Okay. Why? When? How? Okay. You need to ask yourself. Okay. So you are in the mathematics degree, right? You cannot just calculate and then tell me, I know this is 6. You need to try and think about it. Why it is 6? Okay, why at the 6th stage it go back to identity? Why at the 2nd stage they go to identity in different case? Why? Okay, why? Because the order of two groups doesn't have common divisor. Doesn't have common divisor. Okay, good. So let's see. I'll give you this statement here. So the group Zm cross Zn is cyclic. Okay, and is isomorphic Zmn. Okay, if and only if. Okay, we also said there's no common divisor. Okay, meaning what? M and N are relatively prime. Okay, or co-prime. So what does this mean? There's no common divisor. The other way to say it, it is the GCD of M and N is 1. Okay, there's no common divisor. I mean, no common divisor greater than 1. Okay, more precisely. 1 divide everything. So we need to prove this. Okay, we need to prove this. Okay, how to prove this? So let's quickly sketch the idea. So how do we prove this? So let's do one way. Okay, let's say we know that Zm cross Zn is cyclic already. Okay, it's isomorphic to Zmn. Can we show that Mn are relatively prime or not? Okay, how to show that Mn is relatively prime? So if it's cyclic, meaning what? You have an element that has the order m times n. Right? So meaning what? Meaning before that, you cannot go back to identity yet. So you cannot be divided by m or n. Okay. So meaning the order of the generator must be the smallest multiple of both m and n. Okay. Which means what? Which is which is Mn. Okay. So when is it true? When is it true? Okay. So this is only true if GCD of Mn is 1. Okay. Right. Does it make sense? Okay. The order of the generator. Does it make sense? Okay. Yeah. Okay. You must contain. Okay. You must contain and so let me write some more. So you must. So you must. So you must. You must contain. Contain an element with order m times n. Okay. Otherwise, you cannot build your ZMN. Right. You need to have an you need to have the one element, okay, with order Mn. Otherwise, you cannot build it. Right. For example, just now, this Z2 cross Z2. Okay. Can you build Z2 cross Z2 with any element inside or not? Can you build Z2 cross Z2 using 0, 1? Can you build Z2 cross Z2 using 1, 0 or 1, 1? Cannot. Okay, you must contain, okay, an element with order equals to Mn. Okay. And then to do that, okay, to do that, you must have the order equals to the smallest multiple of m times n. Okay. And this is true if GCD is equal to 1. Okay. Okay. How about the other way? Let's say, okay, let's say what? Let's say we already know that m and n are relatively prime. Okay, we want to prove that it is cyclic. We know that m and n are already relatively prime. We want to prove that it is cyclic. Okay, so how to prove it? If and only if. Uh, almost. So you need to find the generator here, right? So first one, I give you the generator. Second direction, you need to find the generator for me. Okay, you want to find the generator for me. Okay, does there exist a generator or not? So you need to find for me. Okay, so if I tell you that m and n are relatively prime already, okay, can you find the generator for me or not? Identity of both of them, or do you mean the generator for both of them? Yeah, you need the generator for both of them. Okay, you need the generator for both of them. Okay, so for example, the case just now. Okay, how do we generate Z2 and Z3? Okay, why these two generate them? Okay, why 1, 1 generate them? Why 1, 2 generate them? Okay, actually you can observe that actually 1 and 1 generated Z2, 1 and 2 also generated Z3. Okay, so you need to prove it. So this is your observation. Okay, you see that it is generated by the n tuples of generators. Okay, so you need to prove it. Okay, so how to prove it? How to prove it? So you can consider first, okay, a value which is mn over d. Okay? So you can take any d, okay, really any d, and then divide mn. Okay, but what happened is this number is always divisible by m and n. Okay? No matter what I put what d. Make sense or not? Because you have a factor of m and n at the top. Okay, so it's divisible by m and n. Okay, so what happened? Okay, if I take all the element in Zm over Zn, okay, what happened? Okay, what happened here? So let's say this d, right? D divides mn. Okay, let's say that this d divides mn, so that this is a integer. Okay, and then we add rs multiple times. Okay, in particular, we want to add it as mn over d. Okay, mn over d such that this is a positive integer. Okay, equals to 0. Okay. So what does this imply here? So what's our goal? Okay, we know that m and n are relatively prime. Relatively prime means what? What's the d we can take here? Who say one? Who say one? What's the GCD you can take here? What kind of d you can take? Huh? M. M. So okay. So what's our assumption here? So assume what? So please remind ourselves, what's the assumption here? So assume the GCD of m and n is equal to 1. Okay. So what kind of d does this m times n over d make sense? Yeah, m times n. Or take d equals to m times n. Okay, sure. Take d equals to m times n. Sure, this one makes sense. Good. Yeah, it really makes sense. But what is m times n over m times n? 1. So if you do Rx one time, you get identity. What's the Rx? Identity. So it's not interesting. Okay, so maybe you want to get some more interesting integer, right? Any more interesting integer you can get on? Huh? No. I mean d. Oh. I mean mn over d. Mn over d. When is this an integer? When is this an integer? Any other d I can take or not? Given that I know that mn GCD is 1. Can I take any d such that m? Okay. I mean, if you cannot imagine, right? Take an example, right? Take an example. For example, just now, okay, don't use the previous example. Use GCD of 5, 7. Any d such that 5 times 7 over d is an integer or not? D equals to 1. Suppose d is strictly so okay. So if d equals to 1, what happen? So if d equals to 1, meaning this is the you will get this Rx as the order of Mn. This is what you want, right? You want the generator, you want the order n element. Okay, if d equals to 1, you are done. Okay, if d equals to 1, you are done. So let me put here. So if d equals to Mn, then Rs is just 0, 0. Okay, so if d equals to 1, okay, of course, just now I suppose d greater than 1 here. But let's say we take, if d equals to 1, what happens? Then Rx to the Mn is 0, 0. Okay. So this is supposingly which is supposingly the generator we want. Okay, what do we want? We want a generator with order mn. Okay, to generate the group. Okay. Any other choice or not?
Can take D either M or
Take D equal to either M or N. Okay, what happens if we take D either M or N? Okay. So if we take D either M or N, what happens? Okay. So if we take D equals to either M or N, okay, what will happen? So let's try. Okay. Okay, I think I want to try it out because otherwise you don't know what this proof is going on. So let's take D equals to Mn. Yeah, let's experiment with the proof. So if I take D equals to M over N, let's just do one, right? Just do one. Okay. Let's do one. Let's see what happens. Mn over M is just N. Okay. Mn over M is just N. Okay. So if this is N, okay, so this order is N, can you make sure that every element go to 0 with this number or not? Can you make sure that every element will go to 0 with this order or not? Cannot. Do you have example? Huh? 1, 0. Okay, so let's do an example. So the question is, can every element, three elements go to identity with order n? Okay, so Soning give an example. So example, Z2 cross Z2, right? Okay, so the Mn here is what? Is 2, 2. Okay, and then the GCD here is, here of course already break the law, right? Is 2. Okay, and then is this a good example or not? You want to do it here or do it different way? Soning. Okay, I think you want to do it with a proper way. So let us do the Z2 and Z3 so that the GCD of 2, 3 is 1. Okay, so this satisfies our condition. Okay, but if you look at Mn over M, okay, what is Mn over M here? 2 times 3 over 2, for example, equals to 3. Okay, but this number here won't get you identity by any elements. Why? Because if you look at 1, 0 to the power 3, you still get 1, 0, which is not 0, 0. Is it? Let me check. Yeah, correct. Okay. Yeah, 1 plus 1 is 2, which is 0, 0 plus 1 is 1. Okay, so that's the condition here. This M over N, right? Okay, need to send everyone back to 0. Okay, I need to send everyone back to 0. Okay, so so what? Huh? Sorry? Lost, lost. Lost. Lost, never mind. Lost, go back here. Go back this statement. Lost, go back to statement again. Go back to the statement. What you want to prove? Okay. We want to show from GCD of Mn is 1, and then show that the group is cyclic. Okay, to show a group is cyclic, what do you need to show? You need to find the generator, okay, with order mn. So how to find it? Yeah, how to find it? Okay, so how to find it? So just now, from what we said just now, from what we see just now, okay. So if you have a generator with order equaling to the group, you won't get to zero before. You won't get to zero before you reach the order of the group. Okay, meaning you won't have order less than the order of the group, right? You see? You see? So the order of group is 6 just now in this case. Okay, your order of your generator cannot be less than 6. It cannot be less than 6. Cannot be less than 6. It cannot be less than 6. Okay. So how does GCD help here? How does GCD help here? How does GCD help here? So what's the problem with Z2 cross Z2 just now? What's the problem with Z2 cross Z2 just now? All the elements has order 2. Why? Why? Okay, I think the most, how about use different example? Maybe use Z2 and Z4. Maybe it's easier to see. Z2 and Z4. Okay. For example, we have 1 here. Let's take 1, 1. 1, 1 is the generator of both group. But why it doesn't generate both group? Huh? Why it doesn't generate both group? Let's think about this. So 1, 1 is the generator of this. 1 is the generator of Z2. 1 is also generator of Z4. But why 1, 1 doesn't generate Z2 cross Z4? Why? Huh? Of course not for prime, but like if you dive into the calculation, what happened? What did you see? What did you see? What happened to this 1, 1 here? It's order 4. Okay, why is it order 4? It is the order of 2 times 4 divided by GCD of 2 and 4. Sorry? LCM or GCD? So this is order 4, right? Wait. Order 4. What's wrong with GCD? What's LCM you mean? You mean the order is the LCM, is it? Yeah, correct. Okay. So why I think of this GCD here? Why I think of this GCD? Because I think of how I add this number together. How you add this number together? Huh? How you add this number together? How you add this number together? Okay. So when does the first entry go to 0? The first entry go to 0 when you add every second time. But the second entry, how to get 0? You add the every 4th time. So when does this second layer and the 4th layer meet? They meet at every 4th time. Okay. Yeah. Any question? Question? Okay. Okay, so come back to this question. So how do you find the generator? Okay, how do you find the generator? Okay, we'll take a break until 10:19, and then we'll see how to find the generator. Okay. Okay, in the meantime, I'll take handles. Venus, 乐天 ，yeah，规则，单鹅，yeah，严苛，OK，泽瑞，Steven，思雨，金生，顺林，yeah，海人，yes，金波讲海人，Wine，yeah，Tishon，yeah，英奇，可以，对，OK，good，雪岩，哎，呀，雪岩，yes，嘉业，嘉业 sick，离开，袁家，陈硕，呀，玉维，陈硕，right，一定，呀，玉维，accent 啊，燕博，OK，陈烨，林晶，呀，广杰，宜州，yes，定宇，呀，柳青，OK，OK，真诚，硕宁，yes，鼓励，倩，德轩，莹，Grace，大叶，嘉文，明修，Michelle， Ryan， Ellie， 雪梅，子源，OK，呀，
这个那个
啊哈，
element 不是 order of the element 被始终是不是小于 order of the group
小于等于，
小于
对，而且可以被除。
所有的 group 来
对 Lagrange theorem 说可以被除啊，小于，如果小于的话，就要是被除，可以被 divide 的数字
这不就可以知道了？
啊，
就如果
呀
空间
啊，
就是他们不管是
它 mn 的话一定会去到零，对不对？啊，然后要论证它为什么不是小于，
如果是小于 m 的，
对，
如果小于 m 的话，那我就一乘以一个小于 m 的数，
个乘以小于2的数啊，对，
怎么说呢？
就是
所以
说
再发现一个，就发现一个大于1小于原文的一个
就是这么说。
common divisor。
你看，如果1对不对？它 m 乘 n 肯定是去到0嘛，对不对？
对啊。
但假设啦，假设它是小于mn，OK，意思说
可以再找一个
bm 或者说 ad，应该这样讲嘛？啊，对，所以它就可能的时候，它会去到 r 去到0 ，such that r 是小于 mn，对不对？
嗯。
然后，因为我们知道这个 r 一定要 divide mn 嘛，所以 r 乘一个可能 p 会小于 mn，对。
可能找到一个
但是如果这样的话，意思是说，
R 也是个 common divisor。
对 r 会小于等于 mn over p，意思说 r 是等于 mn over p，意思说 mn 可以被 p divide，对不对？如果 mn 可以被 t divide 成一个 r 的话，证明说它的 GCD 不适应。
对，先找一个，就直接就找一个那种 order 的一个 element 就可以。
对，
直接找。
对，直接找。但是比较明显的是 ED 或者 generator of 那两个。
就是我11点有考试，所以
11点，
对，
你要走了，
不
你要早走。
就是不能走得太晚，就是
可以，没问题，
4:50之前。
没问题，你走，没事，你走，你可以走。嗯。Oh, before we start, remember I talked about the arting project. I want to type the arting solution now. Yeah. So there's one respondent, Yuwei. Okay, Yuwei said that he want to help and type. Okay, and then Jimbo will be doing the solution, right? I believe he is disciplined, so he can finish the solution. So we have one doing the solution. We have one typing the solution. Okay. Maybe I need some more to type. Okay. And then I want some editor. Okay. What's the role of this editor? Editor have to help and read a solution, whether the solution has gap or not. Okay. We need to fill in the gap. We need to write it clearer, shorter, yeah, so that everyone can read it fast. Okay. Or if you are interested, you can contact me. But I want to invite some of you. Okay. I want to invite, for example, I already invite Li Kai help to type. And then I want to invite Ding Yu, Ziqian, and Yi Ding. Are you guys free or not? Huh? Help with producing the solution. Editing, typing. Yu Wei and Li Kai, for example, they will type. Okay, maybe you guys help and read. You guys okay? You guys free? Not free. No, it's okay. It's okay. If you don't want, it's okay. Never mind. And you let me know. Okay. Yeah, 之前 定义 you guys okay with it? If you got time, okay. Then I will add you into a group, and then we will maybe use overlay to type it, and then everyone can make changes. Okay, and then when all of us happy with the solution, then we can post it up online. And then this will be copyrighted to you guys. Okay? Yeah, because this book is a quite common book, famous book in the study group theory. So everyone will definitely have to refer to this. Okay? But some other, if you want to join, you can contact me. Okay? It's a good opportunity to learn. Okay? Although this is a voluntary book, you are not get paid. I'm not paid as well. Okay, so these are volunteer. You will learn. Okay, you want to join. Even if you just want to as a typer also can. You just type. Okay. People will produce solution, you type, and then some people check. Okay or not? So if you are interested, I will add you guys into a group. so that we can discuss what to do. How to do it. Okay. Okay. Yeah, feel free to contact me. Okay, so come back to this question here. So what's the obvious generator you want to pick to show that it is generated by that generator? What's the obvious guy you want to pick? Good, the generator of both of them. So in this case here, what's the generator of both of them? The obvious one. The obvious generator you want to pick here is what? 1, 1. Good, very good. So we start with that. Okay, you have to start somewhere, you know. So let's start with 1, 1 and then see if we can make it true or not. Okay, if cannot, then we need to identify the problem and then hit the wall again. So in mathematics, you are just hitting the wall all the time until you break the wall. Okay, so we go the other side, right? Okay, so let's say we want to show that 1, 1 is the generator of Zm cross Zn. Okay, this is what we want to show. Okay, so meaning we want to show that the order of 1, 1 is actually m times n. Okay, so nothing much you can do. Suppose for contradiction. Okay, so suppose for contradiction. There's nothing much you can do here. So suppose for contradiction. So suppose for contradiction, the order of m of 1, 1 is less than mn. Okay, so suppose it's less than it. Okay, but why not greater? Why not greater? Why not greater? There are three. Okay, number has trichotomy law, right? Have you guys learned it? Number axiom. There are trichotomy law for numbers. You are either equal to a number, greater or than a number, or less than a number. So if it's not equal, it must be greater or less than. So y cannot be greater. Right? Order and the element is smaller or equal to the order of group. So what law is that? What's theorem? What theorem? Very famous one. Throw a name, maybe you can guess it. There's only one theorem with name we learned in this class, right?
East theorem.
What?
East theorem.
No, no, my theorem. What's the theorem? There's one name with one name. Lagrange. Again, Lagrange theorem says what? The order of the group divide the order of subgroup divide the group. If you take the cyclic subgroup, then it will tell you that the order of the elements divide the order of the group. Okay? If you divide, surely less than or equal to. Okay, so it must be less than or equal to. So now suppose for contradiction, order of 1, 1 is less than mn. Okay, so meaning what? It is equal to some number less than mn. So let's say there's a number p. Okay. Moreover, as what we said just now, this p will divide. So by Lagrange, maybe by corollary of Lagrange theorem. Okay, to be precise, by Lagrange also can. By corollary of Lagrange theorem, p have to divide mn. Okay. So we assume that p is not 1. Okay, we don't want p to be 1. Sorry, we don't want p to be 0. P is non-zero. Okay, good. I'm non-zero. So we say that p is dividing mn. Okay, so meaning what? Meaning p equals to m over n divided by d for some d. Okay, can this happen or not if d is a positive integer? Can this happen? Can you divide m and n such that you get an integer or not? So what's your condition? Your condition is GCD of mn is 1. This d can only be 1 if you want to get an integer. Okay. Does everyone following? Huh? Sorry, question? Console. Cannot be m or n. Can you be m or n? Can it be m or n? The question is, can it be m or n? So can it be m or n? Okay. Can it be m or n? Can it be m or n? Yes. 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 If it is n, okay, so there are few choice, right? Okay, few choice here. So some possibilities, okay, possibilities. Possibilities for p to be an integer. D is 1, m or n. Is this all? Is that all? Sorry? And mn, huh? Okay, good. Anything else? Nothing else, huh? Okay, so we need to rule out this possibility. Okay, let's rule out this possibility. So what if mn equals to 1? The order of 1 can be 1 or not? Cannot. Just now we already discussed what is the order of things that has order 1? Identity. Okay, so cannot be this. Otherwise 1 is the identity of the group. Okay, can it be n or not? If it is n, what does it mean? P equals to n. So meaning what? Meaning your order of 1 is m. Can 1 go to 0 when you take m times or not? Huh? Can 1 go to 0 after you take n times? No, unless what? Unless, sorry, this is m time, right? Sorry, m times. Unless what? Unless more than that. Unless n divide m. Unless, sorry, no, let me think. M divide, unless n divide m. Yeah, unless n divide m, the other way. Okay, so I mean, we can look at example. We can look at example here. So for example, what example should we take? So we should take the real example. So for example, Z2 cross Z3. Okay. So this m and n partially you cannot listen to an abstract argument is you don't have a real mn in your mind. So you need to pick some real mn in your mind. So in this case here, let's pick our m and n, m be 2, n be 3. Okay. And then we look at the generator, the same generator 1 here. Okay. And then we claim that can it be the generator such that mn over d? Okay. So in this case here is 2 times 3 over 3, which is 2. Okay. Can this go to identity or not? Cannot, right? Because what is this? This is just 0, 2. It's not identity. Okay. But when does it go to 0? When does it go to identity? When does it go to identity? Okay. This has to do with the second choice here. Second choice here. When does it go to identity? This is the second choice. Okay. Okay. Only when this guy is less than the number of. So when does it true? When is it true? If this divide m, so they can go to 0 together. Okay. This is an extra question, by the way. This is an extra question. Okay. We already answered that if it is n, it is not identity. Okay, we answered that already. Let's say we want this 2 to be identity. What should I do? What should I do? Okay, this is an extension. What should I do? Okay, we need to make sure our n divide our m so that they go to 0 together. Correct? Okay. Yeah, there are two things what I say. Okay, if you get the first thing, it's good. If you want to get the second thing, even better. Okay. Yeah. Okay. How about m? You think that m is also a similar argument. Okay, if you go to 0 at m, but how do you make sure n go to 0? Okay, if they don't divide each other. Okay, so the m and n has the same argument here. It won't go to 0. Okay, unless one divide the others so that they can go to 0 together. So the only possibility is n equals to 1. Okay. Yeah, so the only possibility is n equals to 1. Okay. Well, my proof of contradiction become a direct proof only. Yeah. Yeah, so depend on how you prove. Sometimes contradiction can turn into a direct proof. Some direct proof can turn into a contradiction. So really there's a lot of way to express your idea. Okay, but you need to pick one. Okay. For like this is like how to say a sketch. Okay, so when you do it in a proper exercise, proper solution, you need to write your idea down. Okay. Yeah. Question? Any question? Any question? Yes. Yes. That's our assumption. Yes. GCD of Mn is 1. So they cannot divide each other. And they cannot have common divisor. It's a consequence of GCD. Okay. Okay. So D has to be 1. Actually, you need to get your P equals to Mn. Yeah. Maybe, yeah, I'll see. Maybe I try organize two kind of proof for you. So I write one with contradiction, write one with direct proof. And then you'll see what's the different way why we can do both these. Okay. I will organize two versions of proof for this case for you to discern what's the difference of doing these two. Okay or not? Okay, so we have proved that 1, 1 is the generator you want. Okay, maybe you can have other generator like just now, right? We also have 1, 2 as our generator. Okay, you can find other, but searching for 1 is enough. Okay, you want to prove existence. All right, so let's keep going. Hopefully, we can finish this subtopic today. So, by the way, this subtopic, if you want to refer, is in the Frale section 9. Okay, so corollary. So we don't restrict ourselves to 2 tuples. Okay, we can do n tuples. We can do n tuples. So if you check for n products of ZMI, okay, this group is cyclic. Okay, n is isomorphic to, you want to get what's the group is? What's this group? So just now Z2 times Z3 is isomorphic to Z3 times 2, right? Z6. How about this? Z to the product of all the MI. Okay. If and only if all the MIs are combined. Yes, good. Pairwise combined. Okay. So you should see some relation between these number theory and group theory. Okay. Yeah. Try and see some relation here. So example here I want to put here is what is Z72? How you understand Z72? This is so big, 72 elements there. How do you study it? Actually, you can just split it into element with 8 element and 9 element, which is Z8 equals to Z9, Z8 times Z9. Okay, so there's only 8 elements here. Okay, the order is 8. The order is 9 here. So in total, you only have 17. But with this group structure here, okay, you will turn it into a 72 elements. Okay, so it's like you use 18 and 19, create a 72 element set. Okay, with what? With a group structure. Okay, okay or not? So we try to break down large group into smaller group. Okay, into smaller group. Okay, make sure you know. Make sure you see there's a coprime here. There's a coprime here. Coprime here. Okay. What else? So, just now you can somehow see the shadow already. Just now. So what's the shadow I'm talking about? So let R1, R2 up to Rn be a positive integer. Okay, so let them be inside a positive integer. Okay, the least common multiple. Okay, so we redefine what's the common multiple, least common multiple, LCM. Okay, of this number is the is the what? Is the order of the positive, is the order of the positive generator of the cyclic group. Okay, cyclic group of what? Cyclic group, cyclic group, cyclic group, the order of the positive generator of the cyclic group. Cyclic group of what? Of all multiples of. Okay, so how do you find least common multiple of a set? Okay, how do you find the least common multiple of a set? Okay, how do you find the least common multiple of a set? Okay, you will follow the process what we do just now. Okay, what did we do just now? Okay, so for example here, okay, for example, so Z2 cross Z2, what's the least common multiple of 2? 2, okay? So how do we find this least common multiple? How do we find this least common multiple? This 2 appears where? Okay, the least common multiple appears where? Appear as the cyclic group generated by the element in Z2 cross Z2. Okay. Okay. And then see again. Okay, see again. So what's the common multiple of Z2 cross 2 and 3? Is 6. Okay. But where do you see 6 inside Z2 cross Z2? Where do you see the number 6 in Z2 cross Z2? Where's the 6? Did you see 6? Yeah. Did you see 6 or not? Did we met 6 or not? There's the 6 here, right? I mean, not in the set, right? Okay, not in the set. I mean, in when we checking out the group property. Okay, checking out the group property of Z2 cross Z3. Okay, yeah. Did you see 6? We met 6, right? Okay. So where do we make 6? This 6 is the order of my generator. Okay, so this 6 is the order of my generator. Okay, of the cyclic group. Okay. Yeah. Okay. any question or not? Any question about this definition? Any question? Okay. You think about it first. We can come back. Okay. So the theorem here is. So suppose A1 up to AN is in the product group. If AI, okay, you know that all the AI have finite order. Okay, finite order Ri in GI. Okay. Then what's the order of A1, the n tuples A1 up to AN? Okay, so we can ask what is the order of this. Okay. So this order is actually equal to the least common multiple of all the Ri. Okay. I will provide this proof later, but not later, I mean later in the lecture notes. But see lecture note. But I want to let you see how we use this. Actually, you already seen it, but let's try and figure out this example here. Okay. So what's the order of this element in Z12 cross Z60 times Z24? Okay. So what's the order of this guy? So meaning how many times you need to add to yourself, okay, to get the identity? How many times? Okay. So you need to imagine. What do you have to imagine? You need to imagine when you get 0 in the first entry, when you get 0 at the second entry, when do you get the 0 identity in the third entry, and then they have to simultaneously get to identity together. Okay. They have to get to identity together. Okay, so that everything is the identity. So what's the number here? So the claim here is this is equal to the LCM of 3, 15, and 12. Okay, let's see why is it 3, 15, and 12. Okay, when does 8 get to 0? What's the order of 8 in Z12? 3, right? Because 8 times 8 is 8 plus 8 is 16. It's not 0 yet. 16 plus 8 is 24. But 24 is divisible by 12, so you get 0. Okay. How about the order of 4 in Z60? Is 15, right? Because if you add 15 times, you get 60. Okay. How about the order of 10 in Z24? It is 12. Okay, it is 12. Because 120 is divisible by 24. 120 is 24 times 5. Okay, so when is the first time they get to 0 together? It is the time when they reach the LCM. Okay, this is the time when all the 3 entries get to 0 together. Okay, so the LCM of these 3 numbers is 3 times 4 times 3 times 5 times 4, which is 60. Okay, yeah. So meaning you need to add 16 times, okay, so that you get to the identity. Okay, you need to add 60 times. Okay, yeah. So in the exam, don't go and try and add this 60 times. Okay, make sure you know how to use this formula. I always tell a story to the class when I teach the discrete math, right? How you expand the binomial polynomial. Like for example, x plus y to the power 2. How you expand it? What's the coefficient? How you get the coefficient? Pascal triangle. Good. So you get a Pascal triangle. 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 4, 1. Right? Let's say I want to ask you to evaluate x plus y to the power 35. What do you do? What do you do? You want to write the Pascal triangle until 35 line? Hey, you don't laugh, huh? You don't laugh. There's one student do that in my class. In the exam.
Why you really come out this?
Yes, he's filled 2 pages with the Pascal triangle. Can you imagine what? Of course, the calculation is too big. Then you got the wrong answer.
Right. For them to expand all the
Yeah, expand until 35. 2 pages. Okay. So what is the definition? So you can actually the definition of Pascal triangle is a combination of the powers and the coefficient that you need. Okay, the term that you right. Okay, yeah. So don't go and add 60 times and tell me the order is 60. Okay, use this LCM. Okay, check the order of each element. Okay, and then find the LCM of them. Okay. This is the first time they will get to 0 together. Okay, this is the first time they get to 0 together. Right. I mean, let's test on a smaller example that we have just now, right? So Z2 cross Z4. Okay, so what's the order of 1, 1? Okay, so this is the order of 8, 4, 10. Okay, order of 1, 1 is what? Okay, just now we said that it is equals to 4. Okay, why is it 4? So this theorem shall use that is the LCM of 2 and 4, which is 4. Okay, so if you imagine what happened here is this guy will get to 0 at the 4th time. The first guy will get to 0 when it is order 2. Okay, so how should you imagine this? So how should I draw this better? So 1, 1, 0, 2, 1, 3, 0, 0. Okay. So this is the first time, second time, third time, and 4th time. Okay. So let me take 1, 1 to the power n. Okay. So LCM is the first time that reach 0 together. First time reach 0 together. Okay, for 147. Okay, maybe I'll state some theorem first. Let's see if we want to prove it next time or not. I want to get into conclusion first, and then we will revise it again next class. Okay. So next theorem is about a product group. Okay. So let's say we have 2 subgroups, right, of a group. Okay, we can define a multiplication map from a product group to the group itself, right? Because we just take products between elements in groups. It still live in the group, okay, because group is closed in particular. And then the image are these HK. Okay, so you have the idea is you have a G. Okay, you have a G. Sorry, you have a G. Okay, oh, cannot see. Maybe let me go. Okay, so you have a G, right? You have a G. Okay, and then you have a H and K. Okay, these are subgroup. So subgroup meaning they have to have at least one intersection at the identity. Okay, so you have a H. You have a K. Okay, and then supposedly they might have some other things here outside here. There may be something inside. Who knows? Okay, and then you take product between these 2 things. So you have H1, H2, K1, K2, and so on. Okay, take the product. Okay, and then obviously, if you take the product, it still live in G. Still live in G. Okay? Maybe it will come out. Maybe it come out outside here. For example, maybe. Who knows? Depend on what group you take. Okay, and then the property here is Or in this case here, maybe I draw the image. So maybe the image will live outside. So this is HK. Okay, G, H, K, and HK. Maybe live outside. For example, maybe H2 times K3 is here. Okay, don't know, maybe. Okay, so the proposition is here. So if this multiplicative is injective, okay, injective if and only if the intersection is only one. Okay, if the map is injective, if the multiplication map HK is injective, then there's only one thing inside this intersection here. Okay, if the multiplication map is injective. And then second, so if I want it to be a homomorphism, okay, if I want the multiplication map to be a homomorphism, why is it a homomorphism? Because H times K, we have shown that as a product under the product operation. G is a group, okay, so both of them are group. When are they homomorphism? If and only if H have to commute with K, okay? Only when H commute with K, I will have homomorphism. Otherwise, this multiplication map is just normal map. Okay, if I want homomorphism, HK has to equal to KH. Okay. Next, if H is a normal subgroup of G, okay, if additionally we know that H is normal, then H times K is a subgroup. Okay, we know that H times K is a subgroup. One of them is enough. One of them is normal, is enough to see that HK is a subgroup. Okay, and then what? And then G is isomorphic to HK. Okay, you see we have homomorphism here. And then when is it an injective? Okay, and then we need another surjective. Okay, so if it is isomorphism, I need injectivity. Okay, first one, the intersection is identity. Surjectivity, HK have to equal to G. I have to reach every G with HK. And H and K are both normal. Okay, you need to have both H and K normal. Okay, then it will be isomorphic. Okay, this is a fun exercise to prove. You can try it. Maybe we can do it together on Wednesday. Okay, and then this will help you to get one result here. Let me see. So we will get this result. There are two isomorphism classes of group of order 4. The class of the cyclic group C4 of order 4 and the class of the Klein 4 group, which is isomorphic to the product C2 cross C2. Okay, so this is what I want we try to get from first lecture, because what I give you two groups of order 4. I ask you to prove that they are not isomorphic in assignment 2, and then now I'm going to show you these are the only two. These are the only two isomorphism classes for group order 4. Okay, with the proposition just now, and then we can further deduce. Okay, every finitely generated abelian group is isomorphic to the direct product of cyclic group in this following form. Okay, so you are either Z to the prime power of primes with a lot of Z. Okay, we have a lot of Z. Infinite group here. Okay, here is a finite group. Finite group cross some infinite group. Okay, we won't prove this last theorem here. We will just state it as a result. We won't prove this because this proof is tedious, very long, but uses the proposition just now. Okay, but we will prove the one with order 2. Okay. But this one is a general result for finitely generated abelian group. Okay, whenever you have abelian group which is finitely generated, then you can write down the generator line, and then use them to generate your abelian group using this structure here, product group structure. Okay, so this is a big result. And for this subtopic, you need to know how to find the order of an element. Okay, using LCM. And then this theorem here we won't prove, just state it as a general result, and then you should take the word. Okay, and then we will prove maybe the theorem for order 4 and then the proposition next class. And then you can try first. It's a very good exercise to do this one. Okay, yeah. This proposition is a very good exercise. Unfolding the definition. Unfolding definition. You can do first, and then we will do it together on Thursday. Okay? See you.